In Chapter 11, we'll learn how to use Lewis structures to predict the shapes of molecules before moving into advanced bonding theories. We'll start with valence shell electron pair repulsion theory, review bond polarity to predict the overall polarity of molecules, then continue to our two bond theories. First, let's learn how to predict the shapes of molecules using the Lewis structures from Chapter 10. We'll accomplish this task in 2 lectures. The learning outcomes for both lectures are identical. There's just a lot of options to cover, so be sure to keep your concepts to memorize sheet handy. Let's begin. Chapter 10 showed us how to construct the 2-dimensional representations of the molecules on paper. However, it's the 3-dimensional shape of molecules that determines their physical and chemical properties. For example, 2 isomers of butanol differ only in where the OH group is located on the molecule. This difference leads to different melting points, boiling points, solubility, and even the temperature at which the molecules will combust. By learning to predict the 3-dimensional shapes of molecules now, you'll be well equipped to recognize the trends in these physical properties at the beginning of Gen Chem 2. We use the valence shell electron pair repulsion model to predict the shapes of molecules once we've settled on their ideal Lewis structure. We do this by counting the number of electron domains, or groups, around the central atom. An electron group can be a shared pair of electrons in a single, double, or triple bond, or it can be a lone pair of electrons, or even a single electron as we saw in our radical-containing molecules. We'll count the number of electron groups around an atom, then use whichever 3-dimensional shape allows those groups to have the most room between them to minimize repulsions. Once we've settled on the 3-dimensional arrangement of electron domains in space, we'll be able to name the electron geometry. Electrons are tiny compared to atoms, so when we're looking at a molecule, we'll only see the influence of the electrons, but not the electrons themselves. When we're only considering the 3-dimensional arrangement of atoms in space, it's called the molecular geometry. Let's start with our simplest case. Suppose that we have 2 electron domains on a central atom. This could be beryllium hydride with its 2 single bonds, carbon dioxide with its 2 double bonds, or even the cyanate ion, OCN-, with its single and triple bonds. Each of these examples will be most stable in a linear electron geometry where the bond angle is 180 degrees to give the maximum distance between the electron domains, which I've circled here. When we move to 3 electron domains in a molecule, they repel each other to form a flat equilateral triangle with bond angles of 120 degrees, a shape that we call trigonal planar. If we consider nitrate, NO3-, the ion has 3 electron domains around the central nitrogen atom, so we say that it has trigonal planar electron geometry and a trigonal planar molecular geometry. Nitrite also has 3 electron domains around the central atom, but one of them is a lone pair of electrons. For this reason, we classify the electron geometry as trigonal planar, but the molecular geometry is bent. While we can't see the lone pair of electrons on the central nitrogen, their influence on the molecular shape is clear. In fact, because that electron pair is not contained within a bond, it will force the 120-degree angle to close slightly, since lone pairs of electrons take up more space than shared electrons. When we move to 4 electron domains, we see the tetrahedron with bond angles of 109.5 degrees allows the most space. When all 4 electron groups are shared in bonds, we'll have a tetrahedral electronic and tetrahedral molecular geometry, as shown here for methane, CH4. If one of the bonded electron groups is replaced with a lone pair of electrons, as in ammonia, here, we'll retain the tetrahedral electronic geometry, but the molecular geometry is described as a trigonal pyramidal shape with bond angles slightly less than the ideal 109.5. Water is another key example. While H2O will have 4 electron groups on the oxygen to give it a tetrahedral electronic geometry, 2 of the electron groups are lone pairs of electrons, so we get a bent structure overall with compressed bond angles. Let's practice what we've learned so far by taking a moment to fill in the number of electron domains, the electronic geometry, molecular geometry, and the predicted angles for each of these molecules. In phosphorus trichloride, we have 1, 2, three 4-electron groups to give us a tetrahedral electron geometry. One of those groups is a lone pair of electrons, so the molecular geometry is trigonal pyramidal, and the bond angles will be slightly less than the 109.5 degrees due to the strong repulsions from the lone pair of electrons. In oxygen difluoride, we have 1, 2, 3, 4 electron groups, giving us a tetrahedral electron geometry. Two of those groups are lone pairs of electrons, so much like water, OF2 will have a bent molecular geometry with bond angles less than 109.5. Finally, dibromodichloromethane has 4 electron groups, none of which are lone pairs of electrons, so the electronic and molecular geometry will be tetrahedral with roughly 109.5 degree bond angles. When bonding groups are non-identical, we sometimes see deviations from the ideal. The shapes of larger molecules are usually described as a series of smaller shapes linked together. For example, in ethanol, we can count the number of electron groups around each non-terminal atom to show we have tetrahedral electronic geometries around both carbons and the oxygen, while the carbons have tetrahedral molecular geometries and oxygen has a bent molecular geometry. Let's try another example. What are the electronic and molecular geometries around carbon atoms A, B, and C? Carbon A has 4 bonding groups, no lone pairs, so the electronic and molecular geometries are tetrahedral. Carbon B also has 4 bonding groups, no lone pairs, so it will be tetrahedral too in the electronic and molecular geometries. Carbon C has 3 bonding pairs and no lone pairs, so it will be trigonal planar in the electronic and molecular geometries. As always, I'll leave you with the parting thoughts of the authors.